This is section 14.3 on partial derivatives. Right, so on page 911 is where it begins, partial derivatives. Now by partial, it doesn't mean that they're half a derivative or something, they're full derivatives, but there's more than one part to it. Okay, so on page 913, now you have the formal definitions, but I'm not going to hold you responsible for them, but they kind of look like what we had in Calc 1. Okay, this f sub x is a derivative with respect to x. Okay, limit h approaches 0, f of a plus hb minus f of ab divided by h. You're basically holding y constant. And similar, a derivative with respect to y, you're holding x constant, f of a, b plus h minus f of a, b all over h. I just mentioned it quickly in passing. Don't worry about it. Don't put it on your formula sheet. But here's the main things that you want to know. So on page 914, for partial derivatives, what you wanted is this box right over here, different notations for partial derivative. So if you have z as a function of x and y, you can't just say the derivative. It depends on whether you take the derivative with respect to x or the derivative with respect to y. Okay. Here are a whole bunch of different notations, and I'll show you the ones that we're going to be using mostly. Okay, so z is a function of x and y. You have x and y. So fx, f sub x, and f sub y, derivative with respect to x, derivative with respect to y. Okay, I'll be using this quite a bit. This is the Leibniz notation, the partial of f with respect to x, or the partial derivative of f with respect to x. It's kind of hard to even say. And what you use is this backwards 6. It's kind of like a funny d. We're used to the Leibniz notation of d, like dy dx, but it's not a full d, so it's kind of like a partial d, you know, very funny, half a d sort of. So backwards 6, partial of f with respect to x. You can have all this other stuff. We normally won't do that. Since normally z is a function of x and y, you can have the partial of z with respect to x or the partial of z with respect to y. Okay, we're almost never going to use these. So the ones that we're going to be using the most are fx, fy, partial of f with respect to x, partial of f with respect to y, and likewise partial of z with respect to x, partial of z with respect to y. So we use the funny backwards 6 for partial derivative. Okay, and you definitely want to use this. It's a pretty simple concept. Okay, to find fx, the partial with respect to x, regard y as a constant and differentiate f of xy with respect to x. And likewise, if you want fy, or the derivative with respect to y, regard x as a constant and differentiate f of xy with respect to y. Okay, so pictorially, here's what's happening on page 915. So here's a function. Z is a function of x and y. So you have the xy plane. Think of the plane of the floor. And it does pass the vertical line test. If you go straight up anywhere in the xy plane, you're only going to touch one point. Okay. This T1, it's the partial derivative with respect to x. You're going only in the x direction. So if I'm only going in the x direction, that means y is temporarily constant, right? You're not moving left to right. And likewise, T2, that's a partial derivative of the function with respect to y. You're only going in the y direction. Rate of change of f or rate of change of z with respect to y. You don't really care about what happens in the x direction. So that means you treat x as a constant. Okay, so you're going to have a function of x and y, or x, y, and z. You hold the other variables as constant. I know it's kind of hard to treat x and y as constant, but temporarily you have to pretend that they're constants like 5 or negative 21 or something like that. Okay. Other than that, that's what you need to know for finding partial derivatives. Okay. Higher derivatives, how do you write it? On page 918. Second derivatives, plural, you're going to have fxx. That means take the derivative with respect to x and differentiate again with respect to x. Okay. Here's the funny Leibniz notation. The funny d squared f over the funny dx squared. So that's kind of like what we did for Calc 1, except instead of d, you have the funny backwards 6. Fyy means take the derivative with respect to y and differentiate again with respect to y, or partial squared f over partial y squared. The mixed partials, fxy, fyx. This means First take the derivative with respect to x. It can be written like this, and then take the derivative with respect to y. This one says, first take the derivative with respect to y, and then differentiate with respect to x. Okay, one thing to watch out for is with the Leibniz notation, you have to go from right to left. Okay, so here, this means x and then y. This means x and then y. So when you see it written like so, partial squared z with respect to y with respect to x, you're going from right to left. You're actually taking the derivative with respect to x first, and then the derivative with respect to y. Likewise here, it's y and then x, which is sort of natural here. For those of us that are, of course, in English, we're used to going from left to right. But here you have to go from right to left. You take the derivative with respect to y, and then the derivative with respect to x. Fortunately, it turns out that for the mixed partials, in almost every case, and in all the cases that we're going to do, it doesn't matter. Fxy and fyx always turn out to be the same for the problems that we would deal with. Okay, so on page 919 is something called Clairaut's theorem. Clairaut's theorem says that fxy and fyx are going to be true whenever this is true, and that happens in all the cases that we will deal with. F is defined on a disk D that contains the point A, B, and fxy and fyx are both continuous on D. You normally don't have to worry about that. All the functions that we will deal with satisfy these conditions. You have to come up with a pretty weird function where fxy and fyx are not going to be the same, which really means, bottom line, you don't have to really worry about, oh, is this xy or is it yx going like this? It doesn't matter. It turns out to be the same for the mixed partials. Mixed partial means x and then y, or y and then x for the second derivatives. Okay. And we're ready to start some problems. Okay, so 14.3, page 923. Okay, and again, for the benefit of those of you that don't have the book and aren't getting it, I'll show you this somewhat quickly. Of course, I'm only showing it to you quickly. It may not be completely focused, but yeah, we're mostly working on the second derivatives, first and second partial derivatives, I should say. So on that, then the next page, try to get this thing focused. And I think you should be able to see everything. Okay. Okay, so 15, f of xy is x to the fourth plus 5xy cubed. So fx, derivative with respect to x, that's no more 4x cubed. Okay, here, 5xy cubed, differentiate with respect to x. That means 5y cubed, that whole thing is considered constant. Treat y as a constant. Its coefficient, 5y cubed, times x. So the derivative is the coefficient, 5y cubed. Okay, how about the derivative with respect to y? Well, x is constant, so its derivative is 0. And here, if I differentiate with respect to y, the coefficient is 5x. So it's 5x times the derivative of the y cubed, which is 3y squared. So 3 times 5x, 15x y squared. 21, f of x is x over y. Let's treat it as x, y to negative 1. So fx, partial with respect to x, well, it's just a coefficient, which is y to the negative 1, or 1 over y. Partial with respect to y, that means x is the coefficient. So it's constant times y to the negative 1. So it's negative 1 times x, y to negative 2. Simplify negative x over y squared. 25, you don't have to f x and y. You're going to have u and v. So g of u of v is u squared v minus v cubed to the 5th power. Okay, derivative with respect to u. So chain rule, 5, blah, 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 to the 4th power, and then times derivative of the inside with respect to u. So 2uv minus nothing, because this doesn't have any u. And a little bit of cleanup, 10uv, u squared v minus v cubed to the 4th power. G sub v, differentiate with respect to v. Starts off the same, 5 u squared v minus v cubed to the 4th power, times derivative of the inside with respect to v. So that means u squared is constant, so the derivative is u squared, and minus 3v squared. 33, function of 3 variables, w equals ln x plus 2y plus 3z. So w sub x, w sub y, w sub z. They all start the same way, right? 1 over x plus 2y plus 3z, 1 over x plus 2y plus 3z, 1 over x plus 2y plus 3z. And then here, times the derivative of the inside with respect to x, 1. And then times the derivative with respect to y, 2, and derivative with respect to z, 3. Here's a function of 4 variables, h of x, y, z, and t. Okay. So differentiate with respect to x. That means all of this is constant. It's constant times x squared. So 2x, y cosine z over t. Okay. At this time, I decided to use the partial, the funny backwards 6 notation for partial derivative. Derivative with respect to y. That means all of this is constant. I just dropped the y. So x squared cosine z over t. Okay, partial with respect to z is a little bit tougher. Think of this as z t to the negative 1. Therefore, this is coefficient. So derivative with respect to z, x squared y, negative sine z over t, times derivative of the inside with respect to z, that's t to the negative 1, or 1 over t. And a little bit of algebra simplification, negative x squared y over t, sine of z over t. Partial with respect to t. So again, x squared y is coefficient, x squared y. Derivative cosine of blah, blah, blah is negative sine, blah, 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 z over t, times the derivative of this thing with respect to t, which is negative z to the negative 2, and a little bit of touch up. 2 negatives make a positive. So x squared y z over t squared, sine of z over t. 39 is not as hard as you might think. U equals square root of x1 squared plus x2 squared plus blah, 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 plus x of n squared. So partial of u with respect to x1, think of this as blah, blah, blah to the half. So 1/2, blah, blah, blah to negative half, times the derivative of the inside with respect to x1. That's 2x1. All of these drop out. 2 cancels a half. So I have x1 over radical. And therefore, all the others work similarly. So I can say, in general, partial of u with respect to xi is xi over square root of x1 squared plus x2 squared plus dot, 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 plus xn squared. Okay, 41, r of st, t e to the s over t, treat that as st to the negative 1. So partial with respect to t, there is a product rule going on, first function, second function. So first, t times the derivative of the second, you copy e to the s over t, and then times the derivative of the exponent floating up here, which is negative s t to negative 2, plus second function, e to the s over t, times the derivative of the first, which is just 1. And a little bit of touch up, negative s t over t squared, e to the s over t, plus e to the s over t. Yes, this can be simplified, but I'm supposed to plug in 0 and 1. And so if I plug in 0 for s, this thing is gone anyway. Put a 0 here and a 1 here, I have e to the 0, which is 1. 43, f of x, y, z is this stuff. They want the partial with respect to y at 1, 2, 2. So first, before I do this, take the properties of logs. Ln of a quotient is ln of the top minus ln of the bottom. Ln 1 minus radical x squared plus y squared plus z squared minus ln 1 plus radical x squared plus y squared plus z squared. And in case you're wondering, no, you can't do anything more with this. So f sub y is 1 over all this times the derivative of the inside with respect to y. So negative 1/2 x squared plus y squared plus z squared to negative 1/2 times the derivative of the inside with respect to y, which is 2y. 2 cancels 2. And similarly here, minus 1 over 1 plus radical x squared plus y squared z squared times the derivative of the inside with respect to y, 1/2 x squared plus y squared plus z squared to negative 1/2 times 2y. That half cancels that 2. So I'm going to have a negative y here, a positive y here. Okay, still very messy, but I'm going to plug in 1, 2, 2. 1 plus 1 squared plus 2 squared plus 2 squared is 9. So that's 9, that's 9, that's 9, that's 9. Okay, y is 2, that goes there. Y is 2, that goes there. 1 minus square root of 9, 1 plus square root of 9. Okay, so this thing cancels out. That's -2 divided by -2. So that's gone. I have 9 to the -1/2, 1 over radical 9, minus, okay, so what do I have here? 2 over 4, right? So 1/2, 9 to the -1/2 is radical 9 on the bottom. So that's 1/3 minus 1/6. Final answer is 1/6. Okay, 53, second partial derivatives. So second partial. So first I need the first partials. What is fx? Derivative with respect to x. That means y is constant, 4x cubed y minus 6x squared y squared. Derivative with respect to y. That means x to the fourth is constant, x to the fourth, minus 4x cubed y. Okay, fxx. Take the derivative with respect to x and differentiate again with respect to x. So 12x squared y minus 12xy squared. Fyy, differentiate this with respect to y, that's nothing. That's considered coefficient, so -4x cubed. And the mixed partials, they should be the same. I did them both just to check. Fxy means take this and differentiate with respect to y. So 4x cubed minus 12x squared y. And yes, they're supposed to be the same, but let's check. Fyx means take this and differentiate with respect to x. 4x cubed minus 12x squared y. And yes, indeed, they are the same. Okay, 57. V is sine s squared minus t squared. So V sub s, cosine s squared minus t squared times derivative with respect to s to s. V sub t, cosine s squared minus t squared times derivative with respect to t, -2t. VSS, take the derivative with respect to s and differentiate with respect to s, product root. So first 2s times derivative of the second, negative sine s squared minus t squared, times derivative of the inside with respect to s, 2s. So a little bit of, then second function times derivative of first, right? So derivative of first is 2, and derivative of this is cosine s squared minus t squared. I'm sorry, that's a copy. Copy the second function times derivative of the first. And a little bit of touch up, that's minus 4s squared sine s squared minus t squared plus 2 cosine s squared minus t squared. Okay, I messed up here. That should be a -2t, 2c. So V of tt is, let's see, first times derivative of second, so -2t, first function, times negative sine, oops, over here, negative sine s squared minus t squared times -2t. So I have -2t times -2t times a -1, because the derivative of cosine is negative. And then plus second function, cosine s squared minus t squared times the root of the first, which is -2. Okay, so cleaning this up, I have a triple negative. So -4t squared sine of s squared minus t squared minus 2 cosine of s squared minus t squared. And then the mixed partial, v sub st or v sub ts, either way, is I can take this and differentiate with respect to t. So that's going to be 2s times negative sine s squared minus t squared times the derivative of the inside with respect to t, which is -2t. And -2t times -2s, positive 4ts sine of s squared minus t squared. Okay. 61, I messed up partially here. Try to, u equals cosine of x squared y. So derivative with respect to x, negative sine x squared y times -2x. U sub y, negative sine x squared y times -x squared. And then let's see what I'm doing. I know, I think I totally messed this up here. Yeah, I know what I did. Start over. I messed up. That's the original function. U sub x, negative sine times this, times the derivative of the inside, right, 2xy. So -2xy sine of x squared y. Yeah, this is totally messed up here. Sorry. U sub y, negative sine of that times x squared. So -x squared sine x squared y. Okay. U sub xy, negative 2xy, cosine x squared y times x squared plus sine x squared y times negative 2x, second time derivative first. Okay. And then u sub yx is negative x squared cosine x squared y times 2xy plus sine x squared y times negative 2x. And if you simplify it all out, you end up with this. So technically, these are the same. They just want you to verify Clairaut's theorem holds for that particular problem. Finally, 63, they ask you to find some third derivatives. fxxx means take derivative with respect to x, then take the next derivative with respect to x, take the next derivative with respect to x. So fx is 4x cubed y minus 3x squared y. fxx is 12x squared y squared minus 6xy. fxxx is 24xy squared minus 6y. And they ask for fxyx. So I already did that. Differentiate with respect to y. So 2 times 4 is 8x cubed y minus derivative with respect to y is negative 3x squared. Then differentiate this with respect to x. So 24x squared y minus 6x. And there we go. Okay, so that was section 14.3.